case you can't tell from his background, his early success was as a rock musician. I don't want to say early success because he actually has an album coming out again. So he is our resident musician, and he does have that dual life. He worked as a mathematics specialist in Los Angeles Unified School District, and he was the head math guy for secondary math in LA for a long time. That's where I met him. He taught AP Physics and AP Computer Science at Van Nuys Senior High. What he doesn't have here, but I like to bring up, is he actually started, I believe, in Great Britain, but at a girls' school. And that was his first teaching job. So he's very passionate about girls and mathematics. He's got degrees in both mathematics and educational administration. And we are so fortunate to have had him for several years here at Mind as our Vice President of Content and Creation. It's a delight to work with him, and you are going to be delighted to hear from him. I'm sure a lot of you already know him, but he's always got new and exciting things to share. So with that, let's go ahead and hear from Nigel, and he's going to talk about the future of transforming math instruction. So Nigel, I'm going to hand this screen over to you.
All right, fantastic. Thank you very much, Deb. I like the fact that you said several years, like, definitely makes me not sound quite as old as I actually am. There you go. I was really trying to do this. We were practicing before so that you wouldn't get to see my messy screen. But unfortunately, all my practice completely failed, and you got to see my messy screen anyway. So there you go. All right. So we are going to look at future of transforming math instruction. I want to pick up actually on, I was sitting in on Steve's session this morning, and I have met Steve on a few occasions, and I've seen him talk and sort of run into him at various places. And even though we actually met again last week as we were sort of planning for this, I didn't know exactly what he was going to talk about. And it was really fascinating hearing him talk, because it almost could not have been a better lead-in for some of the things we're going to look at today. And we're going to look, this whole notion of transforming math instruction, how to, moving into the future. And we're going to look at it in the lens of our new program that has been in development in some shape or form really for the last decade. We've been doing R&D of various types, really exploring this whole notion of, math instruction, how do we move it into the future? But at the same time as we're moving it into the future, what was so fascinating about hearing what Steve was talking about is that everything he was talking about, the sort of lesson style of breaking down these word problems and just changing the delivery, really required zero technology. It just required an approach, right? A methodology, a way of thinking about the content and way of making it accessible for students. So while on the one hand, we've done a ton of R&D and there's a lot of stuff embedded in here, so much of what we've been doing has basically been around this idea of how can we make that type of approach accessible to teachers and relatively easy to do. So it's not that we're trying to do something that's completely bizarrely weird. We're kind of trying to do exactly what he was talking about with InsightMath, and then make it available within a platform in a way that rolls out and is somewhat easy for teachers to do. But I want to start somewhere completely different, and we'll kind of work our way back into that. And I'm going to start with this picture, which when we think about, the future of math instruction, I love this picture. Those of you that have seen me speak before may well have seen me use this because it's just such a beautiful image. This was drawn in 1910 by a French artist, and it was what they thought in 1910 the future of instruction was going to look like. And you can see here, en l'an 2000, in the year 2000, in my best high school French. So there are a couple of issues with this picture in terms of, the teaching methodologies that are sort of embedded implicitly or explicitly in here. So you can see we've got the teacher who is the font of all knowledge, is white and male, and is putting the information from the books, which is the sort of repository for knowledge, into this machine where some kid who for some reason doesn't need educating, probably for some bizarre social reason, is grinding the information up, whereupon it is getting piped directly into the heads of these kids, probably in some perfect personalized learning path or something like that. And this is basically meant to be the, a vision from 1910 of what they thought the future of education was going to look like. So I have a question for you. Type in the chat. I think I can see all chat stuff, including a really fascinating question about where are numbers stored in the brain. Hopefully we'll get to that a little bit later on. But what is wrong with this picture as a vision of education? There are many things, just chuck stuff in the chat. What do you think is wrong as a vision of learning, a vision of education with what we see in this picture? So just put something in the chat, just throw stuff in there. No relationships, love it, thank you very much. Uncollaborative, sit and get, absolutely. Passive, thank you, Amy. It assumes, hang on, oh gosh, this is moving so fast. Right, this is a beautiful one. And thanks, Ashley. It assumes that students sort of can't contribute to the learning, right? The assumption is in this picture that basically what learning is a passive activity where somehow if we can just put all the information in front of the students into their brains through some special kind of device, whatever it might be, that is what learning is. And while on the one hand, and of course there are also no girls in the class, which seems like a minor oversight as a vision from 1910, but it's just fascinating because while on the one hand we can look at this picture and it sort of seems somewhat funny and so forth and so on, it unfortunately bears way too much resemblance to the way that a lot of education looks, and it also bears way too much resemblance to the way many programs are actually designed, where this idea is that, oh, we just put videos and stuff in the system, pipe them at the kids, that magically means they've learned it, and then they can do some worksheets and practice. And that's the vision of education. And I think, Ashley, you mentioned this idea, there's just no vision there that students can somehow be contributors to the learning process. And this obviously is the complete opposite of what we're trying to do. But I know a lot about passive learning because, as Deb said, I actually started my teaching experience here. This is a lovely place called Bruton School for Girls in rural England. And I taught there for a few years, along with playing guitar, which I still do. And then after a few years, I ended up moving to Los Angeles and started teaching here at Van Nuys High School. And everything I thought I knew about how to teach turned out to be completely and utterly wrong. And I want to give you an example of just how wrong I was. I'm going to do the opposite of Steve. Steve kind of talked about, hey, here's how I did this thing and here's how it was right. I'm going to get there, but I'm going to start off by giving you a really good example of how I was really wrong and taught really badly. But here's the thing, while thinking it was brilliant, right? So I had this sort of idea about here's how I have to teach, here's how I have to do it. And it was very much about me sort of explaining, me telling. And I used to use, and I still love this tool. The tool is fantastic. I don't know if you're familiar with GeoGebra. So GeoGebra is a tool that allows you to build mathematical objects. It's a wonderful, wonderful tool. It's also free. It's fantastic. And I love it. But I used to build things like this when I was teaching trig and so forth and so on. And I built this specifically for my students. And it's very cool, right? So basically, it's an interactive manipulative. And you can see here, as you drag this point around the unit circle, you can see this triangle changes. And you can see, oh, the sine of whatever this angle is the length of this side. The cosine is the length of this little side. And you can see that as the angle changes, you can see here all the numbers changing. And of course, because this is a right angle triangle, this squared plus this squared is equal to this. This is a unit circle, so the radius is 1. So this is where our trig identities come from. And okay, here's this one triangle. But hey, wait, there's more, because if you click up here, you see there are other triangles, right? So here's this, oh my gosh, we see tangents and secants, and you can see it's another right angle triangle. So here's where our other trig identity comes from, tan squared plus secant squared equals 1. But wait, there's even more, because if we click up here, there's a third triangle with a cotangent and a cosecant. And again, it's a right angle triangle. The radius is 1. Actually, this in this case, the radius is not the hypotenuse, but you can see this is where our 3 different trig identities go. So my theory of action was that if I, told the kids about this and gave them this thing to kind of play with, that magically they would sort of learn everything about trig identities, and it'd be fabulous and wonderful. And the problem was, of course, that there was somebody in that process who learned an awful lot about trigonometry. I don't know if you want to put in the chat who you think that was. If you, it's a somewhat leading question. It's not a very deep. Yes, me. It was fabulous. I learned a heck of a lot about trig by building this thing. It was awesome. And my students, I mean, maybe a little bit, but unfortunately, the person who was doing all of the work based upon this same theory, the same idea as in that French picture, the idea was I was the font of knowledge. What was coming from me was basically going to be the source of truth, right? And if I basically said it clear enough, then my kids would learn and everything would be great. So it underlied all of my teaching practice. And I had to learn the hard way through basically dealing with this, that actually that was not the best way to teach. That basically me just telling, me creating things, however cute they were, was not the real process. And fundamentally, and obviously you've probably seen me talk about this a lot, it's that shift that happens. I was basically asking myself this question while I was teaching, when I was working at LAUSD as a sort of, I trained math coaches as a district math director and so forth and so on. I was really fundamentally focused on this question. How do we teach? How do I help people teach? And I realized once I walked into a classroom and saw STMath for the first time, I realized within about 2 minutes of watching a penguin go across the screen, I watched a classroom full of sixth grade kids completely engage in problem solving by themselves without anybody kind of like providing the guide rails. They just went for it. And I realized that someone had basically not asked this question. They'd asked this question: how do we learn? And it's that shift that is so powerful and really sort of began. And I have been at Mind now for a bit more than several years. I've actually been here for 13 years. So several is a nice way of putting it, Deb. I'll take that. But 13 years. And really, that 13 years has been in service of this question. How do we learn? How can I figure out more about that? How can I help use my experience to translate that? How can we dive into R&D projects? How can we now build InsightMath? All basically focusing on this idea about how do we learn. So rather than teaching by telling, how can we get information from the students? And we're going to see some of that today in the context of InsightMath, and see a little bit of how this stuff hangs together. But we're going to start, and obviously this is another way of looking at this question: what if we can teach math the way the brain learns? And all of you've seen this, you've seen kids engage. This is basically what I walked into when I, walked into a classroom and saw kids basically doing this problem solving, being fully engaged in this process, and realizing that while obviously the source of truth, if you like, was baked inside the game, the kids were discovering it for themselves, and that change and shift in process was so powerful. So I do have a question for you. You can put this in the chat, because obviously STMath grew out of neuroscience and grew out of a neuroscience project at UC Irvine. And there is some very, very specific neuroscience that, obviously I've done a lot of videos about this stuff. So I'm curious, what is, and I'm not looking for a 50,000 word expose here, but what's the neuroscience behind STMath? Like, what has anybody got any sort of thoughts as to what is some of the neuroscience that kind of works, that we see in classrooms when kids are engaged? And put something in the chat if you have some thoughts about kids being put in novel situations. Spatial temporal reasoning, fantastic. Fantastic. Thank you, Caitlin. Right, lovely. The way we learn is building, manipulating, interacting with what's around us. Absolutely, learning through problem solving. Thank you, Laurie. And so, can anybody who's at Mind then, what is the sort of the more formal neuroscience way of basically saying what Caitlin is saying here, this idea of learning by building, by interacting? What is the sort of the more formal, the perception action cycle? Thanks, Molly. So we have already in STMath, and let me just get my cursor back here, we've got a system that really uses one of our fundamental learning mechanisms, this perception action cycle, and it basically allows, just like Caitlin has said here, this idea by learning, by building, by manipulating, by interacting with stuff, it engages students in that process, and using the perception action cycle, which is something that all mammals use to sort of build sort of images of the world around them, build maps, and build an understanding of how the world works. We utilize that in STMath very, very effectively. And this is one of the really primary learning mechanisms in the brain. So that's awesome, right? We build schema. Absolutely. Thank you, Tammy. Ooh, hi, Tammy. So yeah, we build schema, and ultimately this idea of building schema is learning, right? And we can sort of dig into that a little bit as well. So that's awesome. So STMath does this already, right? Like it already builds schema by engaging students' perception action cycle. And, you know, we've all seen games like this type of thing where you're like, I have no idea what I have to do. Oh, if I drag these onto the line, let's just see what happens. And we get used to this idea of, we don't know. It's like, oh, okay, so I see this thing flipped and that kind of worked, but I don't know. And we can explore, we can kind of play in this space and going, okay, I think I'm beginning to see a pattern now. This kind of thing is going to flip around. And through playing and through exploring and basically through using the perception action cycle, we build a gradual understanding, in this case of like, oh, this skip counting little machine's going to walk down the number line, for example. So we're used to this concept within STMath. So this is the really, really big question. So if that's so awesome, which it is, what's missing? And feel free, put stuff in the chat. What's missing? So STMath does this incredible thing. It builds schema, uses the perception action cycle, which is a fundamental sort of learning mechanism in our brains, in all students' brains, doesn't matter who they are. And that's awesome, right? So what's missing? Okay, fantastic. Yes, let's keep getting some thoughts here. This is good. This is good. So thank you, Laurie. Thank you, Taylor. Yeah, so it turns out that obviously this learning through perception action cycle, and if you like, in a one-to-one way, is a really, really, really powerful part of the learning process. But it also turns out that verbalizing, collaborating is actually another one. And I want to show you a really interesting example of some of the limitations. And this actually came up in a leveling meeting I was in last week. We were looking at STMath. And this is a game where you might not expect kids would suck. But one of the things we analyze very closely in STMath is we analyze, are there places where kids consistently are getting stuck, like a lot? And then we sort of think about why. Is it because of some bad game design on our part, or are they stuck for some schema reasons? You know, like we want to make sure, first of all, that it's not bad game design. And then if they are stuck for some schema reason, can we level into it or out of it more effectively, that type of stuff. So here's a game. Kids basically need to build 100. And not all, some kids will absolutely get through this, but there is a high degree of stuckness, and the kids consistently are doing the same thing. And they will, even after they've seen feedback, they will do this. Can somebody tell me, why are they doing this? What is the issue that they're struggling with here? Hopefully you can all see the screen in enough detail. Yeah, fantastic. So thank you, Kelly, Doreen, Laurie. So what we've got here is obviously they're putting 4 ones and 6 ones correctly together to, there we go, thank you, Amy. That's the word I was absolutely looking for. They put the 4 ones and 6 ones together correctly. They put the 3 10s and 7 10s together correctly. You know, it's like, okay, I get that these things sort of go to make the next decade. What they're not doing is basically then regrouping to go, oh, the 4 and the 6 actually make one of the 3 and 7 thingies, so therefore I only need 2 of them. And it turns out that even with the feedback, and we can look here for a moment, that we can see Okay, the feedback seems fairly clear in the sense that you see that something, doesn't work. Even with that feedback, students consistently, quite a lot of them get stuck here because this whole regrouping idea is a big idea. And I want to look for a minute just as to how big it is, because obviously regrouping is very connected to place value. And then that place value is then connected to unbelievably different and important things, right? Multiplication, subtraction, addition. You cannot do subtraction of sort of multi-digit numbers without that regrouping idea. And it appears in so many things. So if, for example, you have some real challenge and you have a sort of schema that you just have not got about regrouping, then suddenly that is going to affect all of these other things, and suddenly the whole thing can fall apart. So there are some schema that I'm not going to say are more important than others, but they're very fundamental, and we need to make sure that kids tackle them. So, and what this is speaking to, and this goes back to some earlier comments here, perception action schema building is one critical learning mechanism in the brain, but there are others, and one of the other big ones, and here we've called it academic discourse. That's actually maybe not the best way. I think student discourse is probably a better way of calling it, or collaboration, discussion. But it's this idea that literally by being forced to articulate the thoughts that are in your head, you actually create better connections between those ideas. So if you think about how you learned to teach, one of the fundamental ways that you learn to teach is actually by teaching, right? By actually getting out and doing it, by being forced to articulate your thinking again and again and again and all this sort of stuff. You learn how to teach. And it's that this is the mechanism in your brain that is really being utilized as you sort of have to think about, how can I explain this? How can I talk about this? How can I make that happen? By being forced to express your ideas, that actually helps to clarify your ideas and strengthen those schemas. So we need to utilize more than just perception action cycle. STMath is fantastic. It does this really well, but there is then a need to, in addition to that, to access these other sort of learning mechanisms in the brain. And that really, actually, before we get here, is kind of a major driver to the research behind InsightMath, and then also the implementation of InsightMath in terms of what it's doing. So, for example, then this task, this idea of like, okay, how do we make 100, can become something like this, where, oh dear, Gigi has spilled paint on the desk, and now you can't actually see all of this. And I'm just going to look at a slightly better screenshot of this. So now you can ask a class to engage in a discussion like this, where the discussion is, okay, how many more to get to 100? And this is now, well, you tell me what's different about this as a question than how it was presented in the one-to-one gameplay. There's a couple of real fundamental differences here in terms of the way that this question, which is essentially about the same mathematics, but what is different here about the way that this is engaging students? And again, type some stuff in the chat. Take a moment. Noticing and wondering is needed. Absolutely. And very important. Thank you, Amy. There is more than one right answer here. So again, this is very much more you could, the thinking, the numbers, the answers, estimation, approximation. Absolutely. You can see, I know I've got 7 and a bit, 7 tens and some stuff. Okay. And it's through then it encourages splat math. I love it. Yes, it encourages discussion, and now it is that discussion that obviously is going to build the schema. All those kids that were getting this wrong when they were playing the game, it's not like they had no schema. Most of the kids that were getting stuck, they were putting 3 tens and 4 ones. So they had the schema of making tens. They had the schema of making hundreds from things. They just didn't have that regrouping piece kind of going with it. Now, by engaging kids in discussing this type of more open-ended version of a question, obviously now you start building richer schema, making connections between the schema that they have, and suddenly kids are not getting stuck anymore because now they see, they just see it in a sort of deeper way. So it's a funny little example, but it just happened to come up literally last week. And I was like, oh, that's fabulous. Just what an interesting place where suddenly the gameplay is not enough and it just leads naturally into this classroom piece. And I want to then sort of take a little look at the sort of, how can I put it? An overview, if you like, of kind of like, okay, here's what a sort of lesson and stuff and supporting materials looks like in InsightMath. Here's how it kind of hangs together. And this again is just when Steve was talking this morning, I picked a lesson specifically for a couple of reasons, and it couldn't have been better matched to what he was kind of talking about. So I'm going to just sort of look at how these materials hang together for one lesson, and it's a lesson from grade 1, first grade, unit 7, lesson 5, that doesn't really matter, but the lesson's called Getting Home Safe. And the as you can see here, you can see there are 3 sort of boxes down the middle of the screen. That is because the lesson, fundamentally, the actual classroom lesson piece of this is divided into 3 sections. The first section of which, so these are 45-minute lessons for the classroom, and the first section is called a launch. And the launch in this case is a very simple question, exactly like the type of thing that Steve was asking, where we're asking a question that is just designed to get students talking. How do you get home from school? The whole purpose of this lesson is basically the premise is that there's going to be a sub coming in at some point, and we just need to make sure that we capture data. And this, in fact, this lesson is all about data and graphing data and analyzing data. And we're going to capture data to sort of make sure the sub knows how everybody goes home from school. So it's a nice sort of like simple premise, but it starts with such a simple question. Notice that the numbers, the data for this lesson is coming from the students. It's not a question that the data is being pushed at the students from somewhere else. They're the ones who are generating this information. It also has a very sort of SEL component in the sense that it's their contributions that are being valued. So now in a math class, they're the ones who are contributing the ideas and the numbers to the problems that they're going to work on. So I thought that was a lovely, simple start. And then obviously the sort of the meat of the lesson, what we call the explore, is now the teacher sort of facilitates the class as they build a graph using clothes pegs. I had to talk to the team yesterday about this because I was looking at the lesson plan, and as a high school math teacher, first of all, I use the word clothes pegs because I'm British and you call them clothes pins, and I wanted to make sure I was talking about the right thing. And then also I was like, what talk about to me about the clothespins? But it's like, okay, so I got this down, and it was very, very cool. It was like this multi-step process. I'm not going to dive into super detail about this, but the idea is effectively through a few pretty simple questions, the teacher facilitates the class to build a graph using clothespins and some icons and things of the data that they've generated as a class. And then obviously within this lesson, there are questions about who can interpret the graph that they've built. Like, so what does this clothes peg here mean in this position? They also have a real nice thing where intentionally the graph is unlabeled at the beginning. So the students are asked to place their clothespin, but they can't place them because there are no labels. So it sort of drives from the student this idea, well, we have to label these things and then we can graph them. So again, it's just sort of really nice sort of stepping kids through this process of how do you represent data? What does this data mean? And then asking them questions about graphing and so forth. And then at the end of each lesson, so we have a launch, which is some kind of, way of getting into the conversation or the lesson. Then there's an explore, which is generally going to be the guts of the lesson, right? Like in this case, it's building this graph and then asking some questions about the data. And then at the end of each lesson, there's something called a reflect and connect, which could look a little different in different contexts. But in this case, you can see this is lesson 5 from unit 7. So the reflect and connect here is reflecting about what's different in this graph than some stuff that they've been doing in previous lessons. And one of the big ideas here, and this is a big one, think about this, the previous graphs, they've actually been graphing objects themselves, right? So if it says bottle, it's an image of a bottle. Here they're using this clothespin, not clothes peg, clothespin in a very abstract way to represent students. So it's that there's a real subtle shift there. Now, kids in their reflection are probably not going to pick up on all that subtlety. That is fine. But it's just an interesting sort of example of how we sort of do that. And then the cool thing that I think is really fascinating to see is, okay, InsightMath has these classroom lessons, 45-minute lessons, and of course, kids in InsightMath also do STMath. And for example, just to see how this sort of stuff connects, in STMath, there is a game they play where literally they are building graphs, horizontal and vertical, it doesn't matter, of these, in this case, they're graphing, how many shapes go in different things. So they're building these bar graphs. So STMath has tons of opportunities for the kids to, sort of work with the schema building, build the mechanics of what they're doing. And then obviously in the classroom situation, they get to see that unfold in terms of, data that they've done themselves or lessons that sort of take it somewhere a little bit different. And then the other piece of the puzzle, as it were, we have these things called playbooks, which are basically paper and pencil activities that kind of go with this type of stuff. So you can see here, you've got these three different sort of components. There's STMath games, there are classroom lessons, and then there's this kind of paper and pencil piece. And those together basically form InsightMath. That's hopefully gives everybody like a little window into what's going on. There will be a whole lot more to come, but this gives you some sort of idea of what's happening here. And I'm looking at times. Okay, we've got a little bit of time left. I'm going to do one more cool thing, I think. So hopefully this gives you just a snapshot. But I think that the important thing is here, there's a structure. You see how these different components hang together, but also the lessons themselves, they are designed, and our R&D was very much on this, when you talk about what Steve's talking about, how can we build materials that kind of naturally lead a teacher in the direction that Steve is talking about. They don't necessarily mandate the teacher could do this graph in different ways. If people are used to using certain methodologies or used to having kids work in groups, they can use the materials in those contexts. But the materials naturally kind of have a very strong SEL component where, stuff is coming from the kids, the big ideas are coming from the kids. And then also there's a lot of reflection, a lot of discussion, and all that kind of stuff matched with lots of doing of learning with STMath, and then obviously doing of learning in terms of these paper and pencil activities. Okay, 5 minutes-ish. You probably put that there a couple of minutes ago. Okay, so let's just see. I don't know if we have time to meaningfully tackle this question. I'm going to just rush through this. I'm going to do what I would never normally do. I'm going to tell you how cool it is. Normally I wouldn't do that, but the amount of time left. So I do want to look at this one lesson, which is another good example of this idea of where the big ideas are coming from the students. And this is a lesson from 4th grade. It kind of kicks off a whole unit on fractions, but it does so in a very interesting way. So you can see here, you've got these pattern blocks, and you need to find ways of making 1.5. Now, one of the little instructions that's not here, because ultimately it'll be built into the tool, although it's not yet, is that you can only use one of each of these blocks to build your model of 1.5. Okay, so for example, this is a good model of 1.5, right? Hopefully we all see like, okay, we've got 1 here and here's a half. So this is a model of 1.5. And here's another way of doing it. If I was to do something like this is also 1.5, right? Everybody sort of happy with that. And now remember, we can't use more than one of any block. So if I drag a hexagon out and then try and do 3 triangles, ultimately, I'm not going to be able to bring 3 triangles. I'm only going to be able to bring one of them. So the big aha that I would never normally just tell you, but I would let you grapple with it for ages, is that students eventually have to realize that something like this can be 1.5. Can somebody put in the chat, how on earth is that 1.5? And why is that such a big deal? How can the blue and the green one be 1.5? Fantastic. Lovely. So, and actually there's lots of different ways. So for example, we can also do, if we have, let's see if anyone's feeling really cool today. Can anybody tell me how, hang on. No, not that. Can anyone tell me how is this stuff here? How is that 1.5? Anybody want to take a stab at that? How is that 1.5? I think I'm right. I think I'm right. Hopefully I'm right. Yeah. Yeah. How is all that 1.5? Yeah, fantastic. Okay, thank you, Doreen. And obviously, the big, I know I'm kind of at time pretty much. Fantastic. So we've got this whole spatial relationship going on here. And the big idea, of course, is that if you, so for example, if you make this equal to 1, now this is equal to 1/2, which is a totally valid way of thinking. But of course, this can be a 1 and this can be a half. There are actually lots of different ways. Riverside County, I know we found 8, so I think that's the record, but there's all sorts of ways of doing this. But the point is, the lesson here really is about redefining 1, but it doesn't tell you that. The redefining 1 comes from the students. So again, this is this big idea that we're designing a math course where the big ideas are going to emerge from the students' exploration and so forth and so on. And thank you, Mark. Yes, Mark, the trapezoid. Yep. So that's like a half of all of this and so forth and so on. So fantastic. And there's a couple of other cool ways of doing it. All right. As ever, I am talking too much and running over, but hopefully this gives you a little flavor, little bit of a vision as to, well, how this hangs together with ST Math. And, one of our big phrases here that I think is a good one, this idea that learning is built, not transferred, goes back to that picture in the beginning. You can't just pipe information at somebody and hope it's going to stick. Learning happens when you as a learner are actively involved in building the schema. And it's that realization that has to happen that, of course, is such a critical piece of the understanding. So my way of summing that up, if you like, is if the old way of teaching was to make us do math like a machine, the new way is to basically we need kids to understand it so they can build the machines.